Testing. 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 Okay. We're live. It works. Let me turn off the fans real quick. Alrighty. Welcome to another Hupo stream. We got a robotics paper this morning. So this is called Neural Volumetric Memory for Visual Locomotion and Control. This is a highlight from CVPR 2023. I don't know whether that's one of the prizes or whether that just is just the word highlight for the word highlight. But we got a little robot dog here. This is not the Boston Dynamics one. This is a different brand. There's a couple different brands that make basically the Boston Dynamics robot at this point. I think this one might be called Animal. No, this one looks a little bit different. Alien Go. I think that might be the one. Alien Go. Yeah, this looks like it. Okay, so it's an Alien Go robot dog. These things are $80,000. Okay, so not something you can really buy yourself. I guess you could if you really wanted to, but this is still within the realm of kind of academic institutions and company labs, because probably not going to be spending $80,000 on a dog. So they got this $80,000 dog. They have a Intel RealSense camera in the front there. This is a RealSense. This camera is very popular. I have one of these at home as well. This is a structured light camera, which means that it projects a infrared pattern, and then from that infrared pattern it can get depth, and then it also uses its stereo, the fact that it has multiple cameras with some distance apart from each other, in order to give you depth as well. So you have the $80,000 dog with a $1,000 camera, and I think attached to that looks like one of these Intel Nukes, maybe? No, I don't think it's that one. Let's do NVIDIA Jetson. Yeah, it kind of looks like one of these. So this is without the box, but these come inside like a box. So if you look at the back of this robot, it has this kind of metallic box with little antennas on it. It's one of those small computers. Okay, let's scroll through the github.io here. And this is something that kind of I've noticed a trend over papers, right, is that the github.io is becoming more and more kind of the entry point. It used to just be papers, but now everybody makes these very nice little intro GitHub pages. So we see this little robot dog. Here it's moving, right? You can see it in a couple different terrain here. You have the ladders, you have rough terrain. This is the depth, so they switch between the synthesized and then the real depth input. So the real depth input is coming from the RealSense, which is the camera. And you can see how it's kind of noisy, right? This is the system here. We have dog walking over. This is obviously in simulation, so there's going to probably be some simulated training here. It's encoding these into 3D feature volumes. This is a fairly complicated system here, but you have your policy here, so this is indicative of some kind of reinforcement learning. And then the reinforcement learning policy outputs motor commands for the legs So you can look at the little differences, right? Like if you see here, this was obviously filmed on all the same day, but this one was filmed on a different day. And this kind of looks like MIT, which I think is where they made it. Or no, it might be UC San Diego, but MIT CSAIL, which is a pretty good research lab. So a lot of sim stuff here, which makes me think sim to real, right? Normally, the way that robotics works now is you're basically doing everything in simulation. You iterate on your approach, you iterate on your model, you basically train it entirely in simulation, and then you try to zero shot it into the real world. And that used to not work as well as it does now, but kind of the advancement of simulators over time and the availability of compute so that you can train even longer in simulation, and the increased transferability and generalizability of kind of deep learning approaches means that this sim to real has kind of become the paradigm for training things like these robot dogs. Cool, so let's get into the paper here and see what it looks like. Let's open it up in our paper pile here. So if you guys are new to the channel, paper pile is a favorite tool of mine. It's great for papers. And let's go ahead and zoom in, get the right fit. There we go. I think that's the fit we want. We got neural volumetric control. Whoa, something's weird there. Neural volumetric memory for visual motor control, coming out of MIT CSAIL. Why is the highlighting so messed up? April 2023. This is a little bit older now, almost a month old. In our real world environments, they have a couple different unstructured terrains. Our robot uses volumetric memory. So that's kind of the namesake of this paper, and I think probably going to be the most interesting algorithmic contribution and novelty is going to be this volumetric memory. All right, so let's get to it. Legged robots have the potential to expand the reach of autonomy beyond paved roads. In this work, we consider the difficult problem of locomotion on challenging terrains using a single forward-facing depth camera. Right, so this robot has a single Intel RealSense that faces forward. Due to the partial observability, so partial observability basically means that you don't actually know the true state of the world. So inside a simulator, right, you can design techniques inside a simulator that rely on perfect knowledge of the world, right? You know exactly where every single brick is, you have a perfect representation of the position of your limbs. But as soon as you go into the real world, the position of your limbs is not the actual true position of your limbs, it's an approximation, and you don't really know the exact position of all the objects, so it's a partially observable problem, right? And in reinforcement learning, that's called a partially observable Markov decision process, and there's basically additional steps that you have to take in order to deal with that. Robot has to rely on past observations to infer the terrain, so there's some amount of model-based reinforcement learning going on here, right? It's building a model of the world. To solve the problem, we follow the paradigm in computer vision that explicitly models the 3D geometry of the scene and propose neural volumetric memory. Okay, so neural volumes is basically a concept. It's the same concept behind NERFs, where basically, can you train a neural network to store the information inside a volume of space? And a volume is basically just a cube within the 3D space, right? We have 3 dimensions of space in this universe, so that means that a volume, neural volumes, look at this. Right, this is kind of the OG paper out of Meta here, but basically you have a volume of space and then you have a neural net that basically can tell you what's inside that volume of space. And in the case of NERFs, what you want it to tell you is what the color of the pixels are and the opacity and things like that. But in here, in this robotics paper, what they're interested in is actually the content, the kind of like bricks in there, right? What does the terrain look like inside that volume? And that's what the neural net is going to be approximating. A geometric memory architecture that explicitly accounts for the SE3 equivariance of the 3D world. So SE3 is basically the special Euclidean group 3, which is just a fancy way of saying the 3D Cartesian space that you deal with every single day, right? NVM aggregates feature volumes from multiple camera views by first bringing them back to the egocentric frame of the robot. Okay. We test the learn visual locomotion policy on a physical robot and showed that our approach, which explicitly introduces geometric priors during training, offers superior performance to more naive models. So this, take it with a grain of salt. It's very difficult to reproduce things in robotics, right? It's basically virtually impossible. Like, the techniques are so deeply integrated to the hardware that you have available that you can't really benchmark your algorithm against other algorithms very easily, right? So if you have an LLM or you have some kind of detection model, it's very easy to basically benchmark it against other existing detection models because the benchmarks are very applicable. But in robotics, it's basically impossible to do that because every single kind of pipeline and system is very hard coded for the actual hardware and the task that you're specifically doing. Include ablation studies and show that the representations stored in the neural volumetric memory capture sufficient geometric information to reconstruct the scene. Consider difficult locomotion tasks such as walking up and down a flight, tight coupling of perception, because vision is needed to provide details. Problem is also partially observable. Immediately relevant terrain information is often occluded from the robot's current frame of observation, forcing it to rely on past observations for control decisions. Yeah, so there's some truth here where even you as a human, it's like you're not looking at exactly where you put your feet down every single moment. You look kind of vaguely ahead of you, and then you build some internal model of like what the next maybe couple steps are going to be, and then you just execute on that plan of the next couple steps. So the perception and the control loop are on different kind of timescales, right? And I think they have a similar idea here where, hey, let's run the perception a couple steps ahead. We build this neural volume that stores the terrain, and then we basically have a policy that executes actions based on that neural volume memory. While blind controllers that are learned in simulation using reinforcement learning have achieved impressive results, there are clear limitations on how much they can do. So blind controllers are basically controllers that don't have any vision, any perception stack. They're basically just using the position of joints, maybe the IMU, right, the position of the body, things like that. How to incorporate perception into the pipeline to produce an integrated visual motor controller. This makes it seem like nobody's done this before, but people have done end-to-end learning with vision at the beginning and then control at the end. They've been doing that for a long time now, so that's not necessarily new. Egocentric cameras mounted on the robot. Pretty much any camera is egocentric on the robot. I don't know what that means. Egocentric just means it's like from the point of view of the robot. So unless you have like a camera that's sitting outside and staring at the robot. Frame stacking, where the robot maintains visual buffers of recent images. Okay, so one thing you could do is keep track of all the images that you've had so far, and then feed this stack of frames into your kind of visual motor policy. Frame stacking on a moving robot ignores the equivariant structure of the 3D environment. A second but subtler issue is that biological systems do not have the ability to save detailed visual observations. These concerns motivate the creation of an intermediary short-term memory mechanism to fully aggregate streams. Yeah, so basically they don't want to just give the robot the last 10 frames and then ask it to execute actions based on the last 10 frames. They want to create this intermediate short-term memory representation and then have the policy output actions from that intermediate volume representation, which is clever. I think that this is actually reminds me of the method of loci, if you've ever heard of this. So this is a technique that was used in ancient times to remember things. So back before people had books, right, you kind of had to remember things like poems and by memory, and it's very difficult to do that. So what people would do is they would basically build these mind palaces and then traverse through these mind palaces. And what they're abusing is the fact that the way that mammalian memories work, it's like we're very good at storing paths through 3D space, right? Like an elephant, for example, memorizes thousands of trails that it travels every year, and it knows about those trails. And even us humans, we're very good at that too. We're very good at remembering trails through 3D environments. So there's a kind of explicit geometric prior to our memories, right? And this is kind of a similar idea where, hey, let's have a memory, but let's put an explicit geometric prior, like a constraint to that memory that it has to be SE3, right? Which means that it has to roughly represent 3D space. So good idea, and it's very analogous to kind of biological systems. Our architecture consists of a 2D to 3D feature volume encoder. Okay, so there's a couple different parts here. A pose estimator. And then you combine these two and they call that the NVM, the Neural Volumetric Memory. Takes as input a sequence of depth images and fuses them together into a coherent latent representation for locomotion control. We encourage the memory space to be SE3 equivariant to changes in the camera pose of the robot by incorporating translation and rotation operations based on estimated relative poses from the pose network. So this might be estimated relative poses of the robot itself, right? Especially with something like these robot dogs, the problem is that the egocentric camera on this kind of robot is extremely shaky, right? Because it's kind of hard. There's no, like when you walk around, your head is actually kind of making micro adjustments to your gait, so your vision stays relatively stable, right? Same thing with like chickens are very good at this, for example, where when they move, their head actually stays relatively stable because it's visually servoing to be static. But the way that this camera is placed on this robot, it moves entirely with the body. So if the body is kind of flipping back and forth like this, the view is going to be very noisy as well. This inverse transformation allows NVM to align features from the past to the present. Our training pipeline follows a two-step teacher-student process where the primary goal of the first stage is to produce behaviors in the form of a policy. Two-step teacher-student process. Okay, so simulation and then real, is that where the teacher and student are going to come in? After training completes, this policy can traverse these difficult terrains robustly, but it relies on privileged sensor information such as an elevation map and ground truth velocity. Okay, so this is the problem, is that they train their policy in the real world, in a simulation, and inside the simulation you have access to the ground truth ground, right? You know exactly where the ground is, you know exactly where you are, and you don't have that type of information in the real world. So now you basically need to transfer what you've learned in simulation into the real world. Elevation maps obtained in the real world are often biased, incomplete, and full of errors, whereas ground truth velocity information is typically only available in instrumented environments. Hence, the visual motor distillation stage of our pipeline, which still runs in the simulator, we feed the stream of egocentric views from the forward depth camera into the neural volumetric memory. We feed the content of this memory into a small policy network and train everything end to end. Okay. So end-to-end basically means that they're pushing the gradients all the way from the end of the system all the way to the beginning of the system. Right, that would end-to-end is different from training things in pieces, right? So in an end-to-end pipeline, you're pushing gradients all the way from the control all the way through the perception stack. If it wasn't end-to-end, you would probably train those separately. You would have a perception stack, which is trained in a separate process, right? Maybe getting gradients from some kind of classification or bounding box type task, and then you would freeze that perception stack, and then you would train the control stack separately, right? But end-to-end is basically this idea of training the whole thing end-to-end. For completing this, we offer an additional self-supervised learning objective that relies on novel view consistency for learning. The end product of this visual motor distillation pipeline is a memory-equipped visual motor policy that can operate directly on the Unitree A1 robot hardware. Okay, so that's the actual robot itself. A single policy is used to handle all environments covered by this paper. We provide comprehensive experiment and ablation studies and show that our method outperforms all baselines. Okay, I wonder what baselines they actually have access to. Like in locomotion, using the proprioception. Proprioception basically just means the knowledge of your own joint, right? And in simulation, the proprioception is perfect, but in the real world, the proprioception is noisy, right? Sometimes the values that you get from motor encoders and kind of IMUs and different ways of measuring the position of your limbs in real space is going to be noisy and not perfect. Traditionally, controllers are developed with model-based methods. So model-based means you have some model about how the real world operates. So the model doesn't need to be a deep learning based model. It can also just be a physics-based model, right? So if you have a pendulum robot and it knows how much it weighs and it knows how long it is and it uses basically simple physics equations to figure out how much to push, then that's also considered model-based. Just found your paid channel. Reviewed the Village of AI's paper. Cool, nice to meet you, Deadly Data. Just joined the stream. What is this paper trying to solve here? This is a robotic dog paper. So basically they're using a neural volumetric memory. So it's kind of like a model-based reinforcement learning paper where the model of the real world is going from egocentric depth camera into this neural volume, which is like kind of like a weird abstract map of the real world. And then the policy is on that abstract map. However, most model-based methods fail to generalize to unseen environments. In order to attain better generalization and robustness, recent works utilize model-free reinforcement learning to train neural network controllers in simulation and directly transfer learned policies to a robot. This generally does not work well. Model-free reinforcement learning that you do entirely in simulation and then you try to transfer it directly to the real robot, like that's very, very difficult to do, and I rarely see that work well. These methods are able to achieve high level of agility. I don't know about that. Real-world utility, however, is also limited since these blind controllers are unable to perceive the surroundings. In this paper, we propose to integrate perception to facilitate control. Okay. The elevation map around the robot has been used to perform optimization and planning for foot placement. Yeah, so there's a lot of techniques that have very good policies as long as they have kind of this oracle view of the world around them. And that's why in simulation you can make very good policies. But the problem is that in the real world you don't have that. You don't have the ground truth elevation map. But the elevation map obtained in the real world is either noisy or requires a complicated hardware pipeline, right? You need to have some kind of SLAM, right? Simultaneous localization and mapping. Another option is to use depth or RGB images. Hierarchical control systems also propose to utilize depth reading while the low-level controllers still rely on the proprioceptive state of the robot. So I actually had a hierarchical reinforcement learning system for a quadruped. So that'd be really cool if my name is on here. Let me see. Control F. No, my name is not here. Fear? No. Okay. So I am on some papers, but they're not very good, is the TLDR. But one of them was reinforcement learning on quadrupeds, and it was with a kind of hierarchical reinforcement learning scheme. So here we have the main pipeline here. We have our neural volumetric memory, which is this part here, this little Rubik's Cube looking thing. Extracts 3D feature volumes from every visual observation in the near past. Okay, so you have your current depth. So this is the camera on the front of the robot, that egocentric camera. It's giving you a depth, right? Depth images are grayscale. They're a single channel image where basically the more white it is, the further away it is, and the more black it is, the closer it is. So you can see how here, this is basically just the little bricks in front of the robot. You also have prior views. So not only do you have the frame that you are in the current time step, but you also have some buffer of previous time step frames. You're encoding both of them with this volume encoder, which I assume is probably just some kind of generic pre-trained encoder, but maybe not, right? They said they were training this end-to-end, so they're probably pushing gradients into this. From that, you get a feature volume, right? So this is already a 3D object here. They also are encoding the pose, so I think the pose is the position of the camera, the position of the robot, something like that. Some combination of those. SC3 transformation, aggregate, and then all of that feeds into this neural volume memory. So the neural volumetric memory is basically just a representation of the current view and all prior views. So it's kind of like a little world model. Then you have a proprioceptive encoder. So this is an encoder that's going to encode all the knowledge of the robot's limbs and the joints and the position of the joints and the velocity, right? So you have things like the prior actions that I took, right? What my limbs were doing beforehand, joint angle, what the current angle of my limbs is, joint velocity, like how fast my limb is moving, right? Am I about to swing it? Am I not about to swing it? And then a gravity vector, which is basically a vector that points down from the base of the robot, but that also kind of roughly tells you the tilt of the robot. Is this different than Boston Dynamics Doggo Tech? Yes, it is. This is a different one. This is a, let's see, we looked it up before. They mentioned it over here. This is Unitree A1. Unitree A1. So the Unitree A1, here you go. This is different. This is the Unitree Go one. So this is about $3K. $3,000 is pretty cheap. You know, it's pretty good. Wonder what other home education, Unitree Alien Go, this one. I think this is the one they have. 50,000. Pretty good. Excellent sportiness. See, but this one has an integrated camera versus the one that they're using in this paper. It's using a RealSense. You see this? Little Intel RealSense. Good morning, Saif. Okay, so you encode the proprioceptive stuff. You get a little feature vector, which represents the robot itself, the joints, and so on. And the policy, which is what's actually going to decide what actions to take, which in this case are just motor commands for the 12 different little joints here, right? 12 high-performance servo motors, is going to be consuming this NVM and the proprioceptive feature vector. Controllers still rely on the proprioceptive state of the robot. Propose to learn visual RL policies to output the raw joint angles. Okay, volumetric cognitive map. How to represent and understand a 3D scene has been studied by the computer vision community for a long time. Yeah, there's a lot of different priors that you can use and techniques that people have tried to kind of efficiently represent 3D scenes. I would say the neural volumes, right, which is kind of what nerfs are based on, is the most popular approach nowadays. Neural 3D representations. Our work is closely related, where the deep voxel feature representing the entire scene and the camera trajectory are learned from video clips without odometry in a self-supervised manner. Instead of focusing on view synthesis, we aggregate the 3D feature volume to form a short-term memory representation for decision making. Yeah, so NERF papers, what they want to encode within that volume is the appearance of the scene. But here they're not trying to encode the appearance. What they're trying to encode is the geometry, right? The height map of the scene. Teacher-student training. To accelerate training and utilize the privileged information in simulation, follow a teacher-student training paradigm where the teacher policy is trained and distilled into a student policy. Yeah, so this is kind of a new way. This is transfer learning, right? You're basically training something in simulation and then either zero-shotting it into the real world, which would be no transfer, or you're fine-tuning it on some additional real-world data, which would be fine-tuning. But the paradigm they use here is teacher-student, where you're going to have the teacher model is going to be the one that was trained in simulation, and then the student model, which is the real-world model, is going to be basically trained to attempt to mimic the teacher model. We share a similar pipeline where the elevation map-based policies are trained first and the elevation map-based policies are distilled afterwards. Legged locomotion using egocentric camera views is intrinsically a partially observable problem. To make the control problem tangible, our robot needs to aggregate information from previous frames and correctly infer the occluded terrain beneath it. During locomotion, the camera mounted directly on the robot undergoes large and spurious changes in pose. Yeah, there's a lot of movement, right? I'm sure if you looked at a video of what the robot is looking, it just looks like this, right? It's very difficult to see what's going on. Baking in SE3. So SE3 is Special Euclidean Group 3, which is basically just 3D Cartesian space. Applying translation and rotation transformations onto the feature volume before aggregating additional information from new observation. So really all they're doing here is they're saying that this volumetric space should be invariant to translations and rotations, right? Which are the transformations that you can apply to our real world, right? If I take this cup and I move it here, it should be the same cup, right? And if I rotate it, it should be the same cup. So that's just kind of like the underlying truth of our 3D space that we live in. So you can use that as a prior, which forces this neural volume to have similar properties as the real world. An encoder network receives a sequence of observations. Okay, so you have T different observations, or no, N different observations. Your observations go from T to T minus N plus 1. So T is probably the time, N is probably the number of observations. 3D encoder ENC3D, which extracts feature volumes. VTN minus 1. So you have your observation, which is here, right? And then you have your volume encoder, and then you get your feature volume. So those are the three things here. Observation, 3D encoder, and then feature volume. You have a second network, ENCPose, which estimates the relative camera changes in camera pose between the present frame, OVT, and frames before that. So this is the pose encoder here. The pose encoder is looking at the current view and looking at the previous views, and it's telling you like the relative change between those. Okay. Transform the feature volume from the past to the present using transformations. So these are going to be translations and rotations, transformation matrices, right? You have your feature volume. We annotate the transformed feature volume, so once they're annotated, it has a hat. What do they mean by annotations? These canonicalized volumes can now be aggregated together by element-wise sum to produce a fused feature volume VTMs. Okay, so every single one of these prior views has some pose to it, right? And you're basically taking all those views, and you know what the pose for each subsequent frame is, so you can basically use a transformation matrix to map them all to the same global reference frame. And that's largely what you're doing in SLAM too, right? In SLAM, which is the classic robotics problem of simultaneous localization and mapping, you're taking every single observation and mapping it to the same global reference frame, which allows you to build a map over time. And this is kind of roughly the same idea, right? Where if you know the pose, you can take this image, turn it into a feature volume, and then transform it into the global reference frame. This allows NVM to disentangle the symmetry structure of the ambient 3D space from the content specific to the scene. We encourage SC3 equivariance in memory space, right? So SC3 is basically being used as a regularization or as a prior. We provide a detailed description of all the components in the remaining section. Okay, so our 3D encoder takes a 2D depth map and outputs a 3D feature volume. We parameterize this encoder with a set of 2D convolution layers followed by 3D convolution layers. Specifically, we generate a 2D feature map with the shape CHW, so channels, height, and width, using 2D convolution, and then reshape the feature map channel-wise into a volume tensor. Okay, so height and width, they add this depth, and then they almost add this like batch dimension here, C over D. So this is pretty small, D12H6W6, so that's a very small little volume, right? 3D convolution layers are added to further refine the 3D features. So your encoder basically maps from observation space into volume space. Our pose encoder takes 2 depth images and estimates the transformation in the latent space between these. Yeah, so pose encoder takes 2 and estimates the transformation. It outputs a 6D vector representing the camera pose, and we parameterize the pose encoder with a set of 2D convs. The pose encoder is used to estimate the transformation between previous frames and the present frame. Yeah, so this basically just tells you the relative transformation between frames. I feel like doing this directly from camera observations is actually kind of tricky, right? Usually this kind of transformation would be easier to deduce from using the proprioceptive data, right? You have some inertial measurement unit, some accelerometer that's sitting right in the middle of the robot, so you probably know what the pose of the robot is, so you can just take the pose of the robot at every single one of these times, and I can give you the relative transformation between any 2 frames from that information. So the fact that they're choosing to do this with the depth image itself is interesting. How do Tesla cars perceive the environment? Don't they have the same problem? Tesla cars use a bunch of cameras around them. Yeah, all real-world robotics problems are very difficult because they don't have ground truth of their environment. They have to perceive it, right? It's not like a no-go, right? It's not like if you don't have ground truth, you can't do anything. Obviously, real-world robotics, there's plenty of examples of it working. It's just much more difficult to do something in the real world where you don't have perfect knowledge of the environment than it is to do it in simulation where you do have perfect knowledge of the environment. Okay, fusing 3D features. Given feature volumes from different frames and the estimated transformation from different frames, we transform the feature volumes with the corresponding transformation. Particularly for each position in 3D deep voxels, we transform it with this. So this is basically just a pretty standard transformation here. You have a point, you're rotating it, right? Your point is three-dimensional because we live in 3D space. So you rotate it, and then you translate it. You can actually write this as a 4x4 transformation matrix. That's actually the cleaner way of writing this. Since directly performing transformation in latent space might cause misalignment due to the coarseness of the voxel representation. Yeah, this is kind of something we noticed, right? Is that 6x6x12 is actually extremely coarse, right? That's not a very high resolution voxel at all. So here they have to account for that, and they have additional 3D conv layers to refine the transformed feature volume. We then aggregate transformed feature volumes to get neural volumetric memory, VTM hat, where the hat represents the fact that it's been transformed into a global reference frame, surrounding the 3D structure in the present frame by computing the mean over the feature volumes. Okay, so they actually mean the feature volumes? Huh. That's interesting, because up here they said they actually element-wise sum. But down here they say they take the mean. It's kind of weird. Okay. Although the behavior cloning policy, okay, wait up. Let's read this one here. Figure 4, supervised learning. We train a separate decoder to predict the visual observation in the different frames given one visual observation and the estimated transformation between 2 frames. Okay, so this is how they actually train the volume encoder and the pose encoder. So this is not end-to-end, so this is a little bit disingenuous. I feel like they said they trained it end-to-end, but here you see a very clearly not trained end-to-end. Right, this is a self-supervised training with a kind of a reconstruction loss. So basically they add a decoder that goes from this neural volume memory and then tries to decode the current view, right? And then you just have a reconstruction loss that says this image here should match this image here, right? And you can run this. You can basically have your robot walk around, collect a bunch of real-world data, and then use that to train this perception pipeline separately from the control pipeline. So this, to me, is not end-to-end. So a little bit disingenuous there, saying that they train everything end-to-end, because this here means that they're training the perception stack separately from the control stack. So that's not end-to-end. Learning NVM via self-supervision. Although the behavior cloning is sufficient in producing a good policy, being equivariant to translation offers standalone self-supervised for the neural volumetric memory. Because the camera is forward-looking, we can canonicalize feature volumes from earlier frames and use it to predict a camera image taken at larger steps. This self-consistency loss, computed as a pixel reconstruction error, encourages the memory to be SE3 equivariant. For given visual observation history over a short span of time, so you have a set of observations, they call this a history, right? We use the most dated visual observation and predict all frames. Okay, dated just means the oldest one. We extract the 3D feature volume. Okay, so you feed your observation into the 3D encoder, and that gives you your feature volume, V. And you have estimated camera poses for each of the observations. And then we transform the extracted 3D feature volume into different frames. So you get your transformations from your observations, then you use your transformations to map the volumes into the same frame. And then use a decoder to predict the visual observation. So this is the self-supervised part where you map them all into the same frame. That creates the neural volume memory, and then your decoder takes that neural volume memory and then outputs the current view. You use a reconstruction loss that allows you to train these pose encoders and this volume encoder. And then eventually you throw away this observation encoder, right? And all you would use for the actual full system is this NVM. The decoder first reshapes into channel depth, height, width, into shape channel times depth, height, width, and applies 2D convs. Given the predicted visual observation and the original visual observation in different frames, we compute the prediction loss with a pixel-wise L1 loss. So, I mean, there's better reconstruction losses that you can do in pixel space. So, actually, you know what? Why don't we ask... I'm curious. Let's see. What is better than an L1 loss for pixel reconstruction? I want to say focal loss. Let's see. Yeah, it's not the best choice. Let's make this a little bit bigger. L2 loss, okay. It's kind of the easy one. Give me the cooler one. Damn, GPT-4 very slow this morning. Everybody's putting stuff into it. Structural similarity index, that's not a good loss. This is more, people use this for generative stuff, right? Where you want the content to be similar. Perceptual loss is a kind of similar idea where, hey, feed the images into a network, such as VGG, and then take the difference between those. That's also not really what we want. Adversarial loss. The fuck is this? It's just explaining GANs. Okay, this is starting to just like lose track. GPT's getting distracted. All right, either way, pixel-wise L1 loss is a little bit simple. 3D feature encoder and the pose encoder are both trained in this predictive self-supervised encoding task. Specifically, we formulate this 3D representation learning task as follows. So you have your observation, you feed it into your encoder, you get your volume, and then the transformation of that is fed into the decoder, which produces the observation, and then you compare the observation outside of your decoder with the observation that is the ground truth one, and you do the L1 loss. Since the information contained in different visual observations is naturally different, perfect prediction in our task is not feasible. Do you notice any quality differences between ChatGPT 3 and ChatGPT 4? Yeah, ChatGPT 4 is definitely better, especially if you're doing coding. ChatGPT 4 solutions are better. I haven't done extensive testing, but I think there's this guy, Nat Friedman LLM comparison. Yeah. So I've seen this before. This is a tool made by the guy who made GitHub, which is this guy, Nat Friedman. And he basically made this tool where you can compare the output. So you can basically compare GPT-4 to GPT-3 to Llama to all these different things. So yeah, if you're interested on comparing different LLMs, I would definitely suggest this repo. Feature policy and visual motor distillation. Image observations introduce additional overhead and slow training down as much as 40 times. For this reason, we bootstrap the visual motor policy by first training a state space policy that depends on the elevation map. So state space policy basically just means a policy that only takes the proprioceptive data as input, right? We use proximal policy optimization, PPO. This is a classic reinforcement learning algorithm. It's usually the first one that you try. It's pretty much every single reinforcement learning framework has an implementation of PPO. It's very popular and it's stable too. To train a single teacher policy, so this is the policy, is what takes the actions. What that means is the policy is what decides what actions to take at every step, right, within the reinforcement learning framework. The teacher policy is a 4-layer ReLU network, so multi-layer perceptron would be a better way to describe that. To provide terrain information, we include 2 elevation maps, one larger and coarser than the other. So they have kind of like a feature pyramid kind of thing going on here, where they have a lower resolution version of the environment and then a higher resolution version of the environment. The proprioceptive state is 63-dimensional and includes things like the body gravity vector, which is basically just the direction, the orientation of the robot. You have the joint rotations. You have the joint velocities, and then you have the previous action. You have privileged information, 14-dimensional vector of the robot and the environment parameter. So this is the thing that you only have access to in simulation and you don't have access to in the real world. Dense elevation map. I would actually say that angular velocity is actually also part of the proprioceptive state. You can get a pretty good angular velocity and angular acceleration estimate from things like IMU or an accelerometer. But the angular velocity and the linear velocity that you get inside the simulator are just going to be so much cleaner and better. Then you have a dense elevation map with 5-meter spacing, which is only slightly bigger than the robot. So sparse elevation map, 10-centimeter spacing. So this is the kind of like 2 different resolutions of the feature map, which are only in simulation. So basically this, right? So in simulation, you know exactly where all these bricks are, so you can get dense and sparse versions of that. We use the same reward function for teacher training in all environments. The reward contains the following term. So in deep learning, you have a loss function, and usually that loss function is composed of several different pieces, and you combine them together with hyperparameters and weights, basically, that control which loss is more dominant than other losses. And very similarly, in reinforcement learning, you have a reward function, right? And much like you design your loss function, you're going to have to design your reward function. Your reward function is usually going to be some kind of weighted combination of a bunch of different terms, right? So here they have the reward that the PPO, reinforcement learning agent, is trying to maximize is a combination of R forward, R energy, R amp, and R height. And then there's these little hyperparameters here, these weights that are basically just hand-chosen, maybe optimized with a hyperparameter sweep. So you have R forward, which is reward for moving forward. So you have some reward that encourages you, the robot, to move forward. Energy penalty to encourage the robot to use as little torque as possible. So this is something that you see all the time in legged robots, is basically you want the robot to not like use all of its strength all the time, right? So the torque is basically how much strength it's exerting at each of the joints. And you add a regularization term that says try to find solutions that don't have a huge amount of strength. So the robot's not just like wrestling with the environment at its maximum power every time, right? It tries to be very efficient in its movements, especially for something like a robot dog, right? Because I think one of the biggest problems with these robot dogs is that the battery doesn't last very long, right? So if you can reduce the amount of force it's constantly exerting and the amount of torque that it's constantly exerting, that's a way to kind of save on power. Height tracking reward, encouraging the robot to walk while maintaining a specific relative height. And then AMP, encouraging the agent to produce natural gaits. What the fuck is that? So this is a specialized reward. What does natural gaits mean? Let's see. Oh, interesting. This is these guys are badass. Peter Beal, Sergey Levin. These are like reinforcement learning, robotics. Famous people. Adversarial motion priors for stylized physics-based character control. Okay, so that's probably an even more complicated reward function. So the reward that they're using to train this is actually quite complicated. There's like 10 different terms in it, basically. Because this one here, RAMP, is probably itself composed of a bunch of different terms. Okay, comparison between observation spaces. So teacher policy, visual policy. This is the simulation, and then this is real world. So in the simulation, you have joint states, velocity, elevation map, and depth map. And you don't have the depth map. In the real world, you have the joint states, you don't have the velocity, you don't have the elevation map, but you do have the depth map. So you can see how simulation versus the real world, you have different inputs to the network. Given the privileged teacher policy from stage 1, we then distill the privileged teacher policy into the visual policy pi. So the reason they're calling it privileged is because it has access to velocity and elevation map. Our visual policy utilizes proprioceptive state and visual observation for decision making. The proprioceptive state, so this is the joints of the robot, same as we use to train the privileged elevation-based policy in stage 1, while the visual observation contains a sequence of depth images in our experiment with a shape of 64 by 64 from a depth camera mounted on the head of the robot. This is actually quite a small resolution. I think the RealSense camera that they're using can output images at a much higher resolution, but I guess they're downsampling it just to make it run faster. Our visual policy first processes the sequential information in our proposed neural volume memory. They make the shape workout with convolutions. Proprioceptive feature and visual feature are then concatenated and fed into a final network to get the actual action for the robot. The visual policy is trained with behavior cloning. Okay, so this is how they actually do the teacher-student. So in the teacher and student paradigm, right, the student network is trying to mimic the teacher network. So for every single state, or for every input, the teacher network is going to output a set of actions. And then the student network is going to receive basically the same inputs and it's going to be asked to repeat that or output that same action. So behavior cloning is more a term used whenever the teacher is a set of human-controlled episodes. So if you're controlling the robot, right, you would record a bunch of episodes of you controlling the robot, and then behavior cloning would be basically trying to mimic that with a neural network. But behavior cloning I think the terminology doesn't necessarily, it's like, it seems like a bit of a stretch to say it's called behavior cloning when both the teacher and the student are neural nets. And there's no human in the loop at any point. So the loss for behavior cloning is basically just the policy from the teacher should match the policy from the student. P is the privileged observation, which is just this stuff up here. And then O is the normal real-world observation, which is this stuff here. We evaluate NVM on 4 challenging terrains as shown in Figure 2. Our intention is to evaluate the global and local perception ability of agents as well as the robustness of the learned locomotion skills. Our environment consists of stages, including multiple separate stages with gaps of different sizes between stages. So this is the environment that they're doing it on, right? So obviously you have different environments here. You have like uneven big blocks that are separated by bigger gaps. You have smaller smooth blocks. You have staircase. You have just general uneven terrain. So that's one of the advantages of simulation, is that you can basically create whatever environment you want and whatever variety you want. And then here is kind of the real world equivalence of that. Spiral staircase is pretty cool. Obstacles, stairs, stones. Baselines. We compare our method against baselines that do not contain SE3 equivariance priors. Naive CNN, naive CNN RNN, a 2-layer gated recurrent unit. That's old school right there. It's recurrent neural networks are very old school. Loco transformer and multi-step naive CNN. So, okay. These baselines are not papers. This is more of an ablation study than it is of a baseline. Right? Normally when you say our performance, our method beats baselines, you're referring to other papers, other works, and you're implementing the other works and showing that the other papers don't perform as well as your paper. But here, the things they're comparing against are things that they designed, right? Like naive CNN is basically just, that's an ablation study. That's not comparing to a baseline. So I think the wording in this paper is a little bit triggering. Like they say things that aren't necessarily correct. It's a little bit annoying, right? They said the end-to-end when it wasn't end-to-end. They said behavior cloning when it wasn't really behavior cloning. They kind of needlessly call things privileged and non-privileged, which is kind of like needless terminology. Yeah, observation versus privileged observation. And then here they're saying they do a comparison to other approaches, but the approaches that they're comparing to are things that they designed themselves. So I don't know, a little bit too much flexibility here. Simulated results. We evaluate the final policies. What makes a good baseline? To me, I feel like a good baseline should be some kind of system that basically does the same thing as your system, but was written by some other person in some other research paper. And the problem with that in robotics is that it's basically very, very difficult to reproduce someone's work because it's very tightly tied in with the hardware, right? So it's very easy to create a object detection model or a segmentation model and compare it to other baselines because you're both working kind of with the same thing, right? You're both solving COCO or something like that. There's like kind of like a unified benchmark that you can compare against. But in robotics, you don't have that kind of benchmark, so it's very difficult to compare against other people's work. So here what they're doing is they're just comparing against slight variations of their own work. And that's why I think that if you're comparing against slight variations of your own work, that's more of an ablation study. We evaluate different methods, traversing rate and success rate. Okay, so basically how far the robot can walk and whether or not the robot falls. Evaluate all methods, including the privileged teacher policy across all environments. Visual policies are trained by imitation learning. See, and then here, same thing. It's like they called it behavior cloning, and now they call it imitation learning. And imitation learning and behavior cloning are very, very similar, but it's like you're making it neat. You're like they're introducing too much terminology. They're like flip-flopping on the words that they use, and it makes it more confusing when it doesn't need to be that confusing. NVM outperforms all the baselines and all the environments, especially the stones. Surprisingly, it turns out our method traversed a longer distance in the obstacle environment. We conjectured that 3D understanding of the environment helps the agent to keep a closer trajectory since the teacher can exploit. Yeah, so since the teacher network knows the exact elevation map, it can probably push off of like the stones in like kind of an interesting way versus in the real world, right? The real world policy doesn't have that elevation map, so it can't like push off in interesting ways. So the naive CNN doesn't work as well. Naive CNN with the recurrent network doesn't work as well. Here they have an ablation study where they change the dimensionality of these things. So lower dimensionality, higher dimensionality. This is the neural volumetric memory, so a more compressed version of it, a less compressed version of it. You can see how you do kind of lose something by doing the lower dimensional versions of these. Real world results. To validate the performance of our method beyond simulation, we constructed multiple real-world experiment scenes as shown on the right. We evaluated our method in 3 scenes. So they have their stages, stairs, and obstacles as the 3 little environments that they created. Deploy these policies in real-world scenes and record the distance robot moved for each episode. Terminate the episode after a certain amount of time or until the robot reaches the end of the environment. Loco Transformer is shown to be more robust in unseen scenarios. But not the rear legs. Demonstrates a lack of understanding of the surrounding 3D structure. Real-world results indicate that the understanding of the surrounding 3D structure is essential for legged robots to traverse complex terrains in the real world. And our NVM module provides a high-quality volumetric memory of the surrounding 3D structure. Sure. Visualization of SSL task. This is the self-supervised learning. Aiming to gather insight into our learned 3D feature volume, we visualize the synthesized visual observation into our self-supervised learning task along with the present visual observation. The synthesized visual observations are clearly indicating the robustness of our model. Okay, so basically, since you trained the 3D encoder, right? You trained this part here, the volume encoder and the pose encoder, you trained it with self-supervision and you have this observation encoder. It means that you can actually now take this observation encoder and just put it right here in the actual real world and see what it actually gives you, right? And it's going to give you some synthesized view, right? So this is the synthesized output. And actually, interestingly, if you actually remember what ChatGPT said, it says, if you use an L1 loss, it may not always be the best choice as it can lead to blurry or overly smooth results, right? And these guys use an L1 loss, and look at this. Look at the real depth compared to the synthesized depth. It's a lot blurry, right? A lot more blurry, not as clean, the edges aren't crispy. So there you go. ChatGPT making good choices. In the synthesized visual observation, blah, blah, the obstacles in the previous frame are transformed to the position without much distortion. We also note that the reason the decoder cannot recover the details is because the large volumes are clipped. Okay. And look at the input, synthesis, output, so it's kind of blurry, smooth. This is the ground truth. For every tuple, the first image shows the robot moving in the environment. The second image is the input in our visual observation. Obviously, some of the pixels are dropped out. The third image is the synthesized visual observation. And then this is the actual ground truth. Multiple sets of ablation studies. The resolution of the NVM. Our NVM module, right? You can have different resolutions. I think the 6x6 is kind of small resolution, to be honest, right? I feel like they could have gone higher, right? 128 by 128. Granted, it would have been much slower, and I think they want this to run in real time, but how much can you really compress in a 6x6 representation? When the length of visual history increases from 9 to 5, the performance drops. Visual history becomes too long. Okay, so there's also kind of an additional hyperparameter here of how many frames are you feeding into the memory. The compute cost for this, they don't say. It might be in the appendices here. No, they don't mention it here either. So we don't really know what they did this on, but yeah, to your point, RW, compute cost is also very important, right? So it's like the reason they're choosing a very small dimensionality for this neural volume representation, the reason they're choosing to only have the last 5 frames instead of the last 9 frames, like a lot of that is what you're saying. It's also compute cost. It's like if you want this to run on a real robot, right? Like this little computer that's sitting on the back here, which I guess is a NVIDIA Jetson, but I'm not 100% sure and you can't really tell. It has a limited amount of memory, right? It has a limited amount of compute, it has a smaller everything, right? So everything is going to be lower when it comes to the compute budget. So can't do it. You know, we're basically just sitting around waiting for 5G to come out or 6G. And once you have like, I don't know about 5G, but maybe 6G and 7G, right? I feel like running stuff on the edge is actually going to disappear, and that will simplify robotics so much, right? Like, think about how many constraints there are right now on robotics because you have to basically do all the compute on the edge, right? You have to, the computer that's on the robot has to be powerful enough to do everything. But think about how much easier it would be if you could have all that compute in the cloud, and basically there's almost nothing on the robot. It's just like a camera that sends the picture and then receives the action from the cloud. I think the like latency and the speed of that is still just not there. But I think if you project forward like 5-10 years, I think those speed issues and the latency issues will be solved, right? I don't know exactly how, but like some combination of like satellite internet and like things like that. But once you solve those, I think you can start to use much bigger networks, much more compute heavy kind of systems within robots. And I think that's actually what I envision in the future, is when I envision a future of like Optimus robots that are moving around your house and doing things like that. I don't actually see them doing a lot of edge compute. I actually see them doing a lot of kind of cloud-based inference. We propose short-term memory mechanisms, the neural volumetric memory, to enable legged robots to traverse complex terrains with ease. Neural volumetric memory aggregates knowledge from sequential visual observations in the near past by explicitly modeling the translation and rotation between previous frames and the present frame. The explicit modeling of transformation and self-supervised task also encourage the SC3 equivariance in the memory space. They fucking love to say this. This shows our neural volumetric memory provides reliable surrounding 3D structure information for the robot to perform decision making and the new possibility of utilizing visual observations for legged robots. Yeah, and I don't think this is limited to legged robotics either. I think that even in things like pick and place or any kind of robotic manipulation task, some kind of neural volumetric memory seems like a benefit, right? It's like we know that humans and mammals, right, have this kind of prior in their own memory, right? We have I don't know if it's an SE3, but it's definitely an SE2 prior, right? It's grid cells, I think they're called, or something like that. Yeah, that fire at regular intervals as an animal navigates an open area, as allowing it to understand its position in space by storing and integrating information about location, distance, and direction. Grid cells have been found in animals such as rats, blah, 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 and humans. So this is basically the 2D version of this, right? Grid cells in your mammalian brain are basically roughly equivalent to this neural volume, except this one is 3D versus I think the grid cells might be 2D, but they might actually be 3D as well, right? Had similar grid spacing and grid orientation. So having these kind of geometric priors to our 3D, to our memory, is a powerful concept, and I feel like a lot of other robotics problems could benefit from this. So to me, the fact that this is on a robot dog and the depth and all this crap, that stuff doesn't really matter. I feel like that's kind of pretty standard. It's just kind of a cookie cutter version of that. To me, the core idea to this paper is really what makes it great, is this neural volume memory, is the idea of putting geometric priors into a compressed memory representation and then using a neural volume model to basically try to store information in that. But yeah, that's the paper. It's mostly good. I don't like how they kind of mess around too much with words, you know, like I don't like this kind of like privilege observation versus non-privilege. Like, why are you making up terminology just to confuse people here? I don't like the behavior cloning and then calling it imitation learning. I think that I don't like the fact that they call this end-to-end when it's not end-to-end, right? They train it in two parts. The perception pipeline is trained with a self-supervised learning, and then the policy is trained in reinforcement learning. But apart from kind of the weird wording in this paper, I think the main kind of idea, the main high-level concept is very good, and I definitely feel like it's going to be a theme in robotics, these kind of like geometric priors on these memory systems. So that's it. Hope it was interesting. If you guys have any recommendations for papers, feel free to drop on our Discord. And yeah, just if you have a cool paper, put it on there, and maybe I'll read it, maybe I won't. I'm not entirely audience captured yet to the point where I do what my audience says, but you know, I'm definitely inspired. So like and subscribe as always. It doesn't pay my bills. I don't really do this for the money, but you know, it's makes me happy when I see more and more subscribers. Hope you guys have a good week, and see you guys tomorrow.